Hi humans, this is Ix, your favorite alien from Sirius. Perfect. If you're here, it means you've built the sensor and learned how to use it following the detection method by Marsio Salcuni as described in the research, link in the description. So basically, you've got everything you need to follow this video. Now, we're going to learn how to build a full 3D shape of the real magnetic field of a magnet, which, as you'll soon see, shares the exact same shape as atomic orbitals, using multiple 2D scans. It's like giving a magnet a CT scan. Yup, a magnetic CT scan. But wait, from now on, to avoid any confusion, let's stop calling it magnetic field. From this point forward, we'll use the term magnetic orbital as defined in the research. Step 3, detecting magnetic orbitals in 3D. Alright, here's what you'll need. Build this 2-level tool, which is basically just 2 acrylic plates, 4 long fully threaded screws, and a few nuts. That's it. It costs nearly nothing, and it's so easy to build, even a distracted Earthling could do it. Just drill 4 holes into both plates, insert the screws, and lock everything in place with the nuts. Boom. Done. Now if you want to go full Marsio style, you can embed the nuts inside the acrylic plates. That way they won't get in the way when you're using rulers and set squares during scanning. Totally optional though. So what is this weird contraption for? Well, this is the tool that allows you to give your magnet a CT scan. You'll be able to perform multiple 2D scans of the magnet at different distances to reconstruct a precise 3D shape of the magnetic orbital. Cool, right? At first, you won't even need the second level. Just place the magnet directly onto the top plate and scan it like you normally would. This will be the central cross-section of the orbital, where the magnetic field originates from the magnet itself. And yeah, it's usually the widest and most intense one. You guys already know the method. It was explained in detail in the previous video, so let's speed things up a bit. Perfect. You've now created the first layer of the orbital, the central one. Let's start using the tool. Use double-sided tape to stick the magnet exactly at the center of the bottom plate. I recommend drawing the X and Y axes on both plates and making sure they're perfectly aligned with one another. Same center, same orientation. Now, raise the bottom plate closer to the top one until the magnet almost touches it. Always measure the distance at all 4 corners of the tool to make sure the plates stay perfectly parallel, and note that distance down. You'll need it later. Great! Grab another sheet of paper and perform another 2D scan at this new height. As you can see, Marcio's using transparent sheets to show you something extra later, but feel free to use regular white A4 paper. Voila! You've got the second layer of the magnetic orbital. Starting to see the difference? Let's keep going. Now move the magnet down by 1 more centimeter and lock the plate in place. As we mentioned in the previous video, remember this crucial fact. A detection that goes from north to south is not the same as one going from south to north. The geometry of the field might shift entirely. So make sure all your detection sheets follow the same orientation throughout your experiment. Always. No exceptions. Depending on the strength of your magnets, you'll want to adjust the distance for each measurement. The ones you see here are N52s. They're seriously powerful. That's why we can measure fields even from 1 centimeter away. But if you're working with standard magnets, I recommend staying just a few millimeters away to collect enough detail for 3D assembly. Alright, can you guess what comes next? That's right. Move the plane 1 centimeter farther and take another reading, and repeat. The more layers you take at different distances, the clearer and more defined your final shape will be. Perfect. Now go ahead and move the magnets further apart and perform another detection. And please, for the sake of dimensional accuracy, keep marking the detection distances. Those numbers will be vital for the 3D reconstruction later. As you can see, the shapes of the main lobes start to shrink and fade out at these distances, like interdimensional whispers disappearing into the void. As always, lower the bottom plane by another centimeter and take a new measurement. At this point, I'm sure you've got the hang of it, right? Now look at this. At this point, just like in our reference atomic d orbital, we notice that the main bubbles are no longer visible from this distance, but the donut shape is still there because it's bigger and more extended. To reset the sensor without using an external magnet, you can simply tilt it toward the magnets, just like Marsio is doing. Why do that? Well, because in quantum terms, you're actually taking advantage of the shape of another magnetic orbital, one that forms from detection perpendicular to the magnetization axis, and still shows a north polarity at this distance. But don't worry, we're only using it to quickly reset the sensor. No need to overcomplicate things. I'm sure you know exactly what to do next. In this case, Marsio is using an external magnet to reset the sensor, because not even the bubbles of the orbital detected in the horizontal scan reach this far. But be careful. Don't bring it too close to the plane or you'll ruin the whole reading, and I'll have to beam down to fix it myself. Okay, I think that's enough data for now, and there you have it. All the slices stacked up, ready for the next step. Careful though. If you want to do this properly, remember that these slices only represent half of the magnetic orbital. You've only been measuring one side. So ideally, you'd rotate the magnet 180 degrees on its axis, and repeat the entire process. Technically, you could skip that part, since the other half should be identical. But if you're dealing with these asymmetric beasts like we are, and want to be thorough, you definitely need to scan the other side too. Now you're at a crossroads. You can choose to continue either digitally or manually, and Marsio is going to show you both paths. 1. If you go the manual route, you'll be building a kind of 3D sculpture. What do you need to do? Easy. Color each layer according to the polarities you detected, like this. Oh, and one more stellar tip. I highly recommend tracing the outlines of the bubbles with a white marker. It'll make them much easier to see, and trust me, your future self will thank you. And at the end, I recommend wiping the transparent parts clean of any fingerprints. Drill holes into all 4 corners and one in the center of each plate. Make sure they're perfectly aligned. A hammer and a nail can do the trick nicely and all at once. Then grab some wooden skewer sticks and mark the exact distances at which you took your measurements, like you see here. Once that's done, slide each layer into place according to the marks and secure them with a bit of acrylic glue. For extra stability, you can add plastic spacers on the sides, made from the same transparent sheets, just like Marsio is doing. Obviously, the thicker the sheets, the more perfectly aligned your sculpture will be. And voila, you've got yourself a proper magnetic orbital, a 3D revelation of quantum geometries in the macro world. Isn't that super hyper cool? decide to go digital, and I totally recommend it for all you pixel-savvy Earthlings. Gather all your magnetic field scans and transfer them to your computer. But wait, not with a photo. No. Use a scanner, so you'll keep the exact proportions of your drawings intact. That's the only way to preserve the true geometry of the field. Precision is key, remember. Next, import the scans into any drawing or editing software. Photoshop works great, but even Premiere Pro will do the trick. There, you'll trace over them, clean them up, and voila, you're crafting scientific beauty. Once they're all polished and ready, save each one as a PNG. Yes, with transparent backgrounds, don't forget that part. It's important for the 3D layering step. Now take all those gorgeous PNGs and load them into any 3D editing software. Even Paint 3D will do. Because all you really need to do is place the images at different depths, matching the exact distances you used when you took your field measurements. If you followed everything properly, ta-da! Here comes the magic. Isn't it stunning? Okay folks, now you officially have the method to create these astonishing 3D field shapes. But don't forget, this is just the beginning. Everything, and I mean everything, depends on the detection angle. For example, if you analyze the same magnets used to generate this d orbital, but from a direction perpendicular to the magnetization axis, boom, you'll get this shape. If you take a full 360-degree scan around every single detection point, when? Another fascinating structure will emerge. And if you start making two or more magnets interact, oh baby, you'll unlock completely new field geometries, matching other families of known atomic orbitals. Isn't that absolutely mind-blowing? And hey, if you want to see us build more of these forms, whether handmade or digital, just drop a comment. If you have any questions at all, we're here for you. Ask away. Now, I'd like to ask you something important. Usually at the end of a YouTube video, people say, please like, subscribe, and share. But this time, it's different. This information is truly valuable. It deserves to reach as many minds as possible. And only you can help us do that. So please, in the name of science, share this with the world. It's been a real pleasure spending this cosmic moment with you all. See you in the next video. Greetings to all humans from X, your favorite alien.